The resistor has a higher resistance than the connecting leads and causes a reduced electrical current. We can see this in the water pipe that a pressure drop is created because of the narrow part in the middle. The pressure on the left is bigger than on the right. The resistor has a similar effect. Here a voltage drop is created. The relation between the electrical current, voltage and resistance is described by Ohm's law. Mr. Ohm was a German scientist that discovered in 1827 that electrical resistance is equal to voltage divided over current. In this formula, resistance is in ohms, voltage in volts and current in amps. A simple circuit with a battery and a resistor can explain this. The voltage source causes a current which is limited by the resistor. The voltage source is 2 volts and we want a current of 4 amps. So what resistance should the resistor have? According to Ohm's law, the resistance is equal to the voltage divided over current, or 2 over 4 is equal to 0.5 ohms. An example of an application of this simple network is a basic LED circuit. Suppose we want to light a red LED with a 9-volt battery. The LED has a specified maximum current of 30 milliamps. If we directly connect the battery, the LED might burn out instantly. The LED practically doesn't create resistance, so the current will get much higher than the 30 milliamps. To prevent this, we can place a resistor at the positive lead between the battery and the LED. The resistor should have a resistance which is just high enough to reduce the flow of current to 30 milliamps. Using Ohm's law again, we know that the resistance is equal to voltage divided over current, or 9 volts divided over 0.03 amps is 300 ohms. If we now connect also the negative lead and create a circuit, the LED emits a nice red light. Using a resistor for an LED circuit is just one application, but there are numerous other applications and purposes for resistors. To give a complete overview would be absolutely impossible in this short video. There are a lot of different resistor types, all with their own applications, characteristics and construction. Fixed resistors have a constant resistance value and they are the most common type. When people talk about a resistor, they most probably mean a fixed resistor. The picture shows an actual carbon film resistor. Fixed resistors are available in axial and SMD packages. Variable resistors have an adjustable resistance value. Most variable resistors are adjusted by mechanical movement. When they are used as a variable voltage divider, they are called potentiometers. When they are used as variable resistance to control the current in the circuit, they are called rheostats. Digital potentiometers are controlled electronically instead of by mechanical action. A third category are resistors which have a varying resistance dependent on a physical quantity, such as light, temperature or voltage. They are often used as measurement devices. Another breakdown of resistor types can be made according to resistance material and construction. Wire-wound resistors are the oldest type which are still used today. They are constructed by winding a resistive wire around a non-conducting core. They can have very low resistance values and can be produced fairly accurate. Furthermore, they are very durable. A disadvantage is the parasitic reactance for higher frequencies. Carbon composition resistors are constructed with a mixture of a non-conducting ceramic and fine carbon particles. They are also very old and used to be the most common resistor type a few decades ago. Although their properties are inferior to other types, regarding for example tolerance, they are still in demand for certain applications. For example, they have the ability to withstand high energy pulses. Carbon film resistors are widely used today. They are made out of a non-conducting core with a thin carbon film around it. Carbon film resistors have a higher accuracy than carbon composition resistors, but have inferior properties compared to metal or metal oxide film. Metal film resistors have a similar construction as carbon film resistors, but have a metal layer instead of a carbon film. They have a better accuracy, a lower temperature coefficient, and a fairly good stability. Metal oxide film resistors are even more durable and have a higher temperature resistance and reliability than the metal film resistors. Foil resistors have a resistive element of a thin metallic foil of several micrometers thick. They have the highest available precision and stability today. Most axial leaded resistors have a marking with colored bands to indicate the resistance value and tolerance. This resistor is a carbon composition resistor with 4 color bands. The first band gives the first digit of the resistance value. The second band gives the second digit. The third band indicates a multiplication factor, and the fourth band gives away the tolerance of the resistor. You can try to memorize the meaning of each band and color, but you can also use the resistor color code chart to decipher the code. At resistorguide.com you can even find an automatic calculator to decipher the code for you. Using the chart, we see that the first red band has a value of 2. The second blue band is 6. The third band is gray, which means a multiplication factor of 10,000. The golden fourth band means a tolerance of 5%. We know that the resistor has a value of 2.6 megaohms with a tolerance of 5%. You can find a
color code was developed in the early 1920s by an organization called the Radio Manufacturers Association as a standard way of marking resistors and some other electronic components such as capacitors and inductors. In this program we will focus on resistors since that is its primary use today. The advantages of color coding over printed text on physically small components are the inherent increase in marking area, which makes the values easier to read without magnification, and a 360-degree viewing angle, which cannot be achieved with text. Color-coded markings are also more resistant to abrasion. On the other hand, color degradation due to aging, oxidation, and overheating can be a problem. To read a color code is easy. The colors represent numbers. Notice that the numbers form a sequence starting with black for 0, brown for 1, red for 2, orange for 3, yellow for 4, green for 5, blue for 6, violet for 7, gray for 8, and white for 9. Notice that red, orange, yellow, green, blue, and violet are the colors of the color spectrum in order. These are the colors of a rainbow. If you can remember the colors of the rainbow, red, orange, yellow, green, blue, and violet, all you need to remember is that the numbers start with black, the absence of all color, then brown, go through the 5 colors of the rainbow, and end with gray and then white, the mixture of all colors. Another way to remember is to employ a memory aid called a mnemonic, such as big boys race our young girls, but violet generally wins. It is well known that some mnemonics are more memorable than others, but most of these variations, like the infamous Bad Boys version, are often considered inappropriate for classrooms. Other languages have other mnemonics for this color code. A rough translation of the French version is, "Don't eat anything or I'll beat you violently, big animal." Most resistors have 4 color stripes, although some, called precision resistors, have 5 bands. Reading a color code is simple. With 4-band resistors, the first and second colors represent the first 2 digits of the resistance value in ohms. The third band represents the multiplier or number of zeros after the first 2 digits. An exception to this is when the third band is silver or gold. If it is gold, the first 2 digits are multiplied by 0.1. If it is silver, the first 2 digits are multiplied by 0.01. Resistor color codes are like scientific numbers with a mantissa and an exponent or power of 10. The fourth band on a 4-band resistor is called the tolerance band and is either gold 5% or silver 10%. Today 5% is a standard grade resistor. Let's try some examples. Here is a resistor with a color code brown, black, red, gold. The first band is brown, which is 1, the second band is black, which is 0, and the third band is red, so the code is 102. The third color, or red, represents 10 raised to the 2 power, or 100. This is the same as 2 more zeros, so we have 1000, or 1000. The fourth band is 5% tolerance, so a brown, black, red, gold resistor is 1000 ohms plus or minus 5%. Now 5% of 1000 is 50, so this resistor can have a value from 950 to 1050 ohms. Here is another resistor, yellow, violet, red, silver. Yellow is 4, violet is 7, red is 2. So this is a 4, 7, and 2 more zeros. The first 3 colors represent 4, 7, and then 2 zeros. So this is a nominal 4700 ohm resistor. The fourth band is silver, so this resistor has a tolerance of plus or minus 10%. So we have a 4700 ohm resistor with a 10% tolerance. Now 10% of 4700 is 470, so this resistor is guaranteed to be within the range of 4700 ohms plus or minus 470 ohms, or 4230 to 5170 ohms. Here is another resistor, white, violet, black, gold. White is 9, violet is 7, and black is 0. So the color code reads 970. It is a common mistake to interpret this as 970, but remember the third digit is the number of zeros, so 10 raised to the 0 power is 1. The multiplier is 1. There are no zeros appended to the digits 9 and 7, so it is just 97 ohms. The fourth band is gold, or 5%, so this is a 97 ohm resistor with a tolerance of plus or minus 5%. 5% of 97 is 4.85. If we add and subtract that from 97, that means this resistor value has to fall within the range of 92.15 to 101.85 ohms. Another example, yellow, violet, orange, gold. That is 473, or 47 with 3 zeros after it. That is 47,000 ohms, or what we would call 47 kilo ohms, or 47 K ohms for short. This resistor has a tolerance range of 47K plus or minus 5%, which equals 44,650 to 49,350 ohms. Another example, violet, green, blue, gold. This is the code 756, or 75 with 6 zeros after it. That is 75 million ohms. Or we can call it 75 mega ohms, or 75 M ohms for short. Notice the capital letter M. Here is another 4-band resistor with low-valued resistance. Its colors are green, red, gold, silver. Green is 5, red is 2, gold in the third band is a multiplier of 0.1. So the code reads 520.1. And so we multiply 52 by 0.1, giving a nominal value of 5.2 ohms. The fourth band is silver, so this is 10%. 5.2 plus or minus 10% gives us a range of 4.68 to 5.72 ohms. Therefore, to be called a 5.2 ohm resistor with a tolerance of 10%, the actual value must fall between 4.68 and 5.72 ohms. To review, 4-band resistors consist of two color codes representing the first two digits of the number, followed by a multiplier, and then the tolerance band. Not all resistors have a 10 or 5% tolerance bands. Many years ago, some resistors had a 20% tolerance, which was indicated by not having a fourth color band. You might find a 3-band resistor in an antique radio or television. For most applications, 5% resistors, or 10%, is more than adequate, but some requirements a more precise resistor must be used. Precision resistors commonly use a 5-band color code. For precision resistors, the first, second, and third bands give the first 3 digits of the resistance value. The fourth band is the multiplier band. The fifth band is the tolerance band. A brown band represents a 1% tolerance, a red band 2%, a green band 0.5, blue 0.25, violet 0.1, and a gray band represents 0.05% tolerance. For example, the first 3 bands of this resistor indicate the first 3 digits, 200. The fourth band, the multiplier band, is brown for 1, or 10 raised to the 1 power. In other words, just 10. So we get 200 with another 0 after it, or 2,000 ohms as the nominal value. The fifth band is violet, indicating a tolerance of 0.1%. So this resistor has a value of 2,000 ohms plus or minus 0.1%. This resistor is guaranteed to be within 0.1% of 2,000 ohms. To calculate this, we convert 0.1% to a decimal number by dividing by 100, which gives 0.001, and multiply by 2,000 to get 2. So this resistor is guaranteed to be 2,000 plus or minus 2 ohms. It can be no less than 1998 and no greater than 2002 ohms. What has been described in this presentation is the most common ways that color codes are used on resistors. There are other uncommon variations, such as precision resistors with 6 bands, including a band after the tolerance band that indicates temperature compensation, or quality codes that are not standardized. Also, some resistors do not use color codes, but have a number printed on them. This tiny surface mount resistor has 100 printed on it. It uses the same coding system as color codes. This one is 10 with 0 zeros after it, or just 10 ohms. This surface mount resistor has 151 printed on it. That would be 15 multiplied by 10 raised to the 1 power, or 15 times 10. In other words, 15 with 10 after it, 150 ohms. Surface mount resistors are sometimes called SMT, surface mount technology, or SMD, surface mount device resistors. Surface mount technology